Okay, so I think we can start. In the last two lectures, we kind of introduced or discussed about what is a Gaussian process, uh, how it is a generalization from a Gaussian distribution, how it looks, what are the different factors, parameters, hyperparameters of a Gaussian process, and some visualization, right? And that is all we did. But we did not really talk about how you can use Gaussian process as a surrogate model. How you can use Gaussian process as a supervised learning, machine learning model, as a regression for solving regression problems. We did not discuss that. So the idea today is to go into that trajectory, to discuss how Gaussian process can be used for solving regression problems. That is what we will be primarily be doing today. But to do that, we will need to know certain concepts about Bayesian statistics, in specific about prior likelihood, posterior marginal likelihood, posterior predictive, and all those things which I have not discussed. We have not reviewed it when we are doing statistics. So the idea is that we will do Gaussian process, and as we do Gaussian process, we will bring in these terminologies and explain them. As a result, we will move little slow and we will take diversion. So for example, if I bring up prior, we'll start talking about prior and then come back. If I bring likelihood, we'll start talking about likelihood and then come back. And in the process, we will be discussing about Gaussian process regression, or how to use Gaussian process or kriging for building a surrogate model. So that is the primary idea for today. We might not be able to complete it today because we will be taking diversion, but at least we will do, let's say, 50% of what we have to do, right? Okay. So with that background, let us start with a reminder or a review of the definition of Gaussian process. So can someone remind me what is a Gaussian process? A collection of no, a collection of random variables, any finite number of which follows a not just any Gaussian, consistent Gaussian distribution. So they will have a pattern, there is some correlation structure and all those things. So a Gaussian process is a collection, potentially infinite number of, so collection of random variables, any finite number of which follows a consistent Gaussian distribution. Okay, so Gaussian process, so it is a collection of random variables. It is a collection of random variables, and this collection of random variables is potentially infinite. Any finite number or set of which, any finite number of which follows a consistent Gaussian distribution, right? This is the definition that we have been discussing for last two lectures. I am just writing it today, but this is nothing new. We have discussed it in the last two lectures as well, right? So this is the Gaussian process, and this is the formal definition of Gaussian process. If someone asks you, this is the definition, you are going to tell them, but we also know that Gaussian process is the generalization of Gaussian distribution to infinite dimension or to function space, whatever you like to call it, right? So it's a distribution over function. It's a distribution over function. What does it mean to be a distribution over function? It means that each sample you draw will be a function. You can imagine distribution over an elephant. If each sample you draw is an elephant, a black elephant, a small elephant, a big elephant, a white elephant, so something like that. So in this case, distribution over function, each sample you draw is a function, right? So it's a distribution over function. Okay. But the question that I posed at the beginning of the lecture is that how are we going to use it for solving regression problem? How are you going to use it as a surrogate model? How are you going to use it as a supervised machine learning technique, right? So how to use GP for regression. This is primarily what we will be discussing today. Yeah. Any finite number of means infinite collection. Remember that it was a function over time. You can select any number of time and those jointly will be Gaussian. That's what it is. Infinite, you cannot have a distribution over infinite, right? You cannot have a distribution over infinite number. In mathematical terms, that does not exist. So you have to always look at finite sets. So that's why. Okay. So how to use GP for regression? Before we try to go into this, let us first try to write down the problem statement for regression. So can someone tell me what is the problem statement for regression? What is the problem statement? What are we trying to solve in regression? First, what is given? You are given data, XY data. Given that what is the objective of regression? You want to build a model that can be used for predicting Y for a new X. So that is the problem statement, right? So this means given D, which is the collection of data set, let's write Xi, comma Yi, that is Xi is my input variable, Yi is my output variable. In the reliability context, Xi are my random variables, Yi are my, let's say, limit state. And I might have n t such samples, right? Given this, we want to build a model that can give, or that can produce or give, right? One of the two things, right? The first thing is that it should either be able to provide you with Y star for a new input X star. That is, it should be able to predict your Y for a new X, right? And this you are aware of, this is the ideal. What is the other thing? Or, can you tell me what is the other alternative? I slightly mentioned it in one of the questions last time, but what is the other alternative it can do when we will call that it is a regression model? No, that's, then in that case I will call Xi plus 1 as Y. So that doesn't, you were saying something? Distribution of Y star given X star and X and Y. So that is known as a predictive distribution. So the name is predictive distribution or posterior predictive. Probability of, it can Y star given X star comma X comma Y. Okay. So when you will train or use a probabilistic machine learning model or a Bayesian machine learning model, that will give you the B, the second one. There you do not get a point estimate Y star, you get a distribution of Y star conditioned on X star and the training data. Why training data? Because if the training data changes, your model changes, as a result your prediction changes. So even the trend, it's a function of training data. It's not independent of the training data. Okay. X star is the input, obviously it should be dependent on that. Y star is your output. Okay. And this is known as the predictive distribution or the posterior predictive distribution. Both are same thing. Okay. Predictive distribution is the more popular one because it's smaller. If I can do that, if predictive can do the task, why will I add a new term, additional term posterior, right? So predictive distribution or the posterior predictive. Okay. So the first A is the deterministic way of doing things. B is the probabilistic or Bayesian way of doing things. Now probabilistic and Bayesian are actually not synonym. There are other ways of making things probabilistic. So to be, if I'm more specific, it is the Bayesian way of doing things. Okay, clear? So what is the predictive distribution? It is the probability of the prediction given the input at which we want the prediction and the training data. Okay. Yes, because if you do an ensemble, you get a probability, but you don't get this product, this one. So Bayesian is a special case of probabilistic. In Bayesian, actually, you get this prior, likelihood, posterior. These concepts are Bayesian concept, but everything that is probabilistic need not be Bayesian. Bayesian is one way of doing probabilistic. It is not the only way of doing probabilistic. That's why I said that. Okay. Ensemble is also probabilistic. That's not Bayesian. For example, Monte Carlo dropout is the probabilistic way you get a distribution during inference, but that's not Bayesian. Although there are some papers which draw parallel between the two, but that is not necessarily Bayesian. So that's why. Okay. This is clear? Okay. So this is what we will like to do, right? In Gaussian process also, we will like to, given that x and y, I will like to find out this distribution B. How will you do that? We'll come to that later. Okay, later means in a short while. Okay, so now, so basically we are interested in learning this model. We are interested in learning or building this model. That is what we are interested in, right? So we are basically interested in building a regression model, right? So how do we model it? So modeling, how to build this model. In any regression algorithm, you build a model as follow. And this is the first step of anything, and then the assumptions comes into picture. But the first step is that you assume that your T, which is a target, and target is generally a function of x, where x is your input, is equal to y of x, which is your model, plus epsilon, which is the discrepancy, the difference between t and y. And this discrepancy comes because of n factors. If you assume those n factors to be IID, right? Identically distributed, I mean independent and identically distributed, or right? And then add it up, you assume them to be additive, then this epsilon will follow what distribution? Gaussian distribution. That is known as the central limit theorem. If you have many IIDs, no matter what the distribution, you add them up, the resulting distribution is always Gaussian. You take 20 uniform distribution, 0 to 1, add them up, you will get a Gaussian distribution. Okay, that is the central limit theorem. So assuming that this holds, this epsilon is generally modeled as a Gaussian. So it's like a Gaussian noise, right? With zero mean, because your model is unbiased, and sigma y square. Remember the sigma y from last time? It comes into picture now. This is the sigma y that I was using last time when I was showing the covariance kernel, right? So this is that sigma y, which is the model discrepancy. Okay. Any doubt on this one? Repeat.
Can you explain this?
T, so basically you have some data, right? So I had this y and x, right? Assume this y you will have will not be y, this will actually be t, because your data will not be actual model output but some noisy measurements, it will be t. So target you have y you cannot measure, y is the actual model output. So and what is the difference between the two? There is some noise, some discrepancy, and that is modeled as epsilon. Okay. Now generally you will not write this t x and y x, I mean this is equivalent to, you will write as t is equal to y plus epsilon. I mean it's given that t is a function of x and y is a function of x, so you can drop that. Okay. So now for a second let us talk about linear regression, or let us talk about polynomial chaos expansion, or let us talk about response surface method. What were we doing in response surface method? In response surface method we are assuming this y is w0 plus w1x plus w2x square. That's what we are doing. So we are representing this y as a parametric model, parameterized by the weights, so that our objective was not to find out y, but to find out the weights, w's, the unknowns. That is exactly what we did in response surface method. What did we do in polynomial chaos expansion? Same thing. We again parameterized it, but we said, okay, your model will be little better if instead of using x1, x square, you use the orthogonal basis. But the w's were the unknowns, and in the non-intrusive version at least, those w's were the parameters of my model, and we were trying to find them from the data. Not in a probabilistic way, but we were trying to find them. So if you realize, till now whatever we have done, we are trying to model this y in a parametric form. Parametric form means there will be some parameters that we will try to find out, and those parameters are not function of the amount of data you have. Whether you have n data or 2n data, the number of parameters remain the same. You make a choice at the beginning, and that does not change with the number of data you have. That is known as parametric model. Gaussian process unfortunately is not a parametric model, or fortunately, it's a non-parametric model. Okay, which means you will not have these parameters w's directly. In fact, in a non-parametric model, the ideal definition is that you have infinite number of parameters. Okay, but that does not work like that. So what happens is that your number of parameters is a function of the number of data point you have. So your number of parameters grows with the number of data. How can you relate it to Gaussian process? In Gaussian process, what do you think are the parameters? In Gaussian distribution, what are the parameters? Mean and sigma. In Gaussian process, it will be parameters. Mu, which mean was a Gaussian, right? That will become mu, which is x, which is a mean function. In Gaussian distribution, you have a mean vector or a mean scalar. In Gaussian process, you will have a mean function. It's a distribution or function, correct? And you will have a covariance kernel. Now this covariance kernel, kx, x prime, if you have n data, the dimension of this covariance kernel is n square. There is symmetry and all those things, I am not counting it, but n square. If you have 2n data, it is 4n square. So the number of parameters is increasing with the number of data. Obviously, we will not try to find these parameters, that's a different story. But you can understand that the actual number of parameters in a Gaussian process increases or changes with data points. So that's why that's a non-parametric model. The difference between parametric and non-parametric is clear. In parametric, the number of parameters is fixed. If your data increases, reduces, it does not change. In non-parametric model, the number of parameters increases with the number of data, and that's why we say it has infinite number of parameters in some sense. Okay, clear? Gaussian process is a non-parametric. So this was the first diversion I took. Let's come back. So t is equal to y plus epsilon, where epsilon is a Gaussian distribution from the central limit theorem. Okay. Now in Gaussian process, it's a non-parametric model. We are not going to represent y as some w transpose phi or something like that, because if we do that, we are parameterizing it. So we don't do that. Okay. So we don't represent this y as some w and phi kind of business. Okay. So we'll do something else. We'll directly try to work in the y space and the t space. Okay. And for that, I now need to reintroduce two more terminologies. Okay. The first terminology I'm going to introduce is, so I'm not writing it, but remember that I already talked about parametric versus non-parametric. We have already discussed this, right? It's kind of not that difficult, so I'm not writing it. The important thing here is that GP is a non-parametric model. This is important. And now the next thing we are going to talk about is likelihood. Can anyone tell me what do you understand by likelihood when you hear this term likelihood? Not the formal definition, not what you've read earlier, but suppose you do not know and you hear the term likelihood, what rings a bell? How likely is something, right? And whenever you say how likely, that means there is also something that is unlikely. That means it is not certain. That means there is a sense of probability itself embedded into the term likelihood, right? How likely means how probable. I mean, that is a synonym in that sense. So likelihood is what? Likelihood is generally represented as, in a normal sense, probability of data conditioned on the parameter. In a normal sense, forget about this expression, I'll come to that later. A likelihood is probability of D, which is my data, calligraphic D, given theta. Theta is my parameter. Let's take an example. How likely is it that a coin will yield head? Right? That means you are trying to find out probability of head. What is my parameter theta? P. Right? You have tossed the coin in number of times. Got some head, tail, head, tail, I don't know. What is probability of D given theta? It is D is your observation, head, tail, head, tail, head. That is your D. Give condition on P, which is theta. Correct? That is your likelihood. And this likelihood will have a form. In the coin tossing example, this likelihood will be Bernoulli distribution, product of multiple Bernoullis, IIDs. Alright, n IIDs, so n Bernoulli multiplied. Let us give one more example that I give always actually. This is my native example, you can say, or go-to example. So suppose Diwali is coming, right? You want to go home. Your parents know you are coming home and you know that, right? Suppose your house is in Rajasthan, right? Jaipur, Rajasthan, let's say, okay? Now you can decide to go home using different modes of transportation. You can decide to take a flight, you can take a train, you can take a car, public transport bus, too much adventurous walk. Possible, right? In theory. Okay, that's why I took Rajasthan. Walk, I mean, you will walk for what? 3 weeks maybe, and you will reach there. Okay, possible, right? Now, when you are leaving IIT Delhi or hostel or whatever, you call your parent that I just left, I just started. Okay, and suppose you reached home in 5 hours. Okay, in between there was no communication. What will your parent think? How did you travel? By car? That takes 5 hours to Jaipur, I think. 8 hours, I think. But anyways, by car or something like that, or maybe train. They will not think that you have walked, right? Because you reached in 5 hours. How are they arriving at this conclusion? Think about it. How did they arrive at this is how you travel? This is the most likely way you have traveled. How did they arrive at that? It is, if you, correct, they have the earlier experience, you are right. But current experience they also have, that it took you 5 hours. That is the data they have, and they have earlier also. So what they actually calculate is probability travel time is equal to 5 hours given you walked. That probability is 0.000001. Probability, it took you 5 hours. Conditioned, you took a train. Probability of 0.45. Probability, it took you 5 hours given that you took a private car. 0.4, 0.45, something like that, right? Probability, it took you 5 hours given you took a flight. There is no direct flight, you have to do all those things, again, very low. So this is what goes in your mind. And then they see, okay, these two are the most likely ones. Now out of these two, okay, I know from the past experience that he or she generally takes a train, so it's a train. That's how our brain arrives at a decision, right? So basically what happens in all these processes, we just estimated the parameter. The parameter in this case was your mode of transportation. And we estimated the parameter based on the data, which was your travel time. So fundamentally, what did we do? Our brain unknowingly it computed the likelihood and took the parameter corresponding to which the likelihood is maximum. So it maximized the likelihood. This is known as the maximum likelihood estimation, or MLE. Right? So this is known as the maximum likelihood estimation, or MLE. So you form the likelihood and then maximize the likelihood to find out the parameter. And likelihood by definition is probability of data given theta. Data given conditioned on parameter. And that is what you will try to maximize or minimize the negative of that. It is the negative likelihood, right? Likelihood. Is it clear? Any question? Yes. In this case, the parameter was the travel time. Now it is coming very soon that there is no parameter, non-parametric model. What are you going to maximize? I mean, if that is your question, it is coming very soon. I mean, if I was doing let's say I was doing polynomial chaos expansion and you want to do a probabilistic version of polynomial chaos expansion, then it was easy. I'll calculate probability of t given x, comma, theta. Theta is a w, and maximize it to find out the parameters theta, which is the weights and biases. In that case, that is easy. In this case, what we will do, I am not going there. We'll go there maybe in another 2, 3, 5 minutes. But right now, what I want you to understand is what is likelihood, and more importantly, what is maximum likelihood estimation. So is the likelihood clear? Or is there any question on doubt, any query on likelihood? Likelihood is fine. So likelihood is generally defined as probability of d given theta. This is your data or observation. This is your parameter. Okay. So this was the likelihood. Now let us go to the above expression. Let's call it equation 1. Let's call it equation 1. Now from equation 1, what is unknown? Because parameters is something, yeah, go ahead. Model, right, let's say. Why is the model? Okay. And that data is obviously noisy. Okay. Okay, so parameters are generally unknown, right? So what will likelihood mean in equation 1? Now let us come to that. What is unknown in equation 1? And what is data in equation 1? What is E and Y? What is that was not the question. What was the question? What is the parameters are generally unknown. What is unknown in equation 1? y is unknown, right? Also, sigma y square is unknown. You know it's noisy, but you don't know the variance of the noise, right? So those are the unknowns, right? What is known? T and x. I'm not written it, but x is also known because xt is the pair. So what will be the likelihood then? Probability of t given y comma x comma sigma y square. Correct. Only on that. No, you cannot, right? It's like you go to fill in measurements, right? So this one, this yi is your ti, I said, right? So this, you have nt such data points. Okay. So those are the only measurements you have. Intermediate ones are the ones I want to predict, hopefully, right? Okay. So the likelihood for this will be probability of t given y comma x comma sigma y square, right? That is the likelihood. Now generally x and sigma y square we often drop, we do not write. T given y is what we write, but in reality it is t given y comma x comma sigma y square. Okay. So from equation 1 we define the likelihood as follows. So probability of t, and remember you have nt such observations, keep that in mind, given y. This is what I will normally write, but because I am writing it for the first time, even those which are obvious I will write them, comma x comma sigma y square. X is data. X is the data because t is at some x. There is no meaning t given y if x is not known. You know t only at given x. It's a supervised learning, right? So t is always associated with x. So whatever x you are taking, the corresponding t, and you are trying to find out the corresponding y. You can put it like that, right? Okay. What will be this distribution look like? Do you know the form of this distribution? Probability of d given theta. Theta is unknown. How is it conditioned? Whatever is conditioned, I'm not saying everything will be known. Y is not known, but y is conditioned. But does not mean everything will be unknown also. Some things can be known also, right? What is the distribution from here? Gaussian, because I have conditioned on y, so y becomes a constant. So it's a Gaussian. Gaussian parameters. Zero. It will be t given y will have 0. What is the mean? Expectation of y. Why expectation of y? Y is conditioned on, so y is deterministic when something is conditioned on. So what is the you don't know that. What is mean of t? What does it even mean? You're trying to find out. Let's see. Let me write something and then let's see. Gaussian, you said of t, obviously. T is the variable. But what condition on or the parameters of this t? What are the parameters? What is the mean and what is the covariance? There are two things. There will be mean, there will be covariance. What is the mean of this? And what is the covariance? Why mean of y? Why should it be mean of y? Am I? You are forgetting a very basic thing in conditional probability. In conditional probability, what is being conditioned on is a constant. So I have conditioned on y. That means y is a deterministic thing now. Y is to be treated as deterministic as long as it is on the conditional side. So it's constant. What is expectation of a constant? So what is the mean? Not expectation of y. y. No, it will not give y. Very soon it will not give y. So the mean will be from here y. What is the covariance? Sigma y square. Is that enough? How many data I have? Nt. So what is the dimension of t? Nt. Y dimension is Nt. Covariance dimension will be Nt across Nt. Sigma y square is 1. Where is that Nt cross Nt? You assume the samples to be IID. So the covariance will be diagonal. So sigma y square is correct, but it should be multiplied by a INT, whatever you call it, right? So sigma y square INT. This is your likelihood, and this likelihood is based on the fact that I have used the central limit theorem to assume epsilon to be Gaussian. If epsilon is not Gaussian, this distribution will be that distribution because y is constant. Let's say epsilon is student's t, then my likelihood is student's t. If epsilon is Laplace, then likelihood is Laplace. So that is governed by whatever distribution you have taken for epsilon, because the y part is constant, right? In likelihood only, right? This is fine. So this is my likelihood. In maximum likelihood estimation, what do we do? What do we do? I just now discussed. What is the point of maximizing this to find out y? Is it even meaningful? Because I will find y at only those NT locations, but I don't want y at those NT locations. I want a model that can predict y at new locations, right? So is there any point in finding out y? It's pointless. There is no point in finding out y by maximizing this. Your ultimate goal is to find out y. That's a different story. But trying to find out y by maximizing this is pointless. You will get y at those NT points, and that is meaningless because you will not be able to predict now y for a new x, which is the actual goal. You will not be able to find a probability of y star given x star comma x comma y. Is it making sense? Y maximum likelihood cannot be directly used here because it's a non-parametric model. If it was a parametric model, then there instead of y I would have written W transpose phi x. In that case, finding out W is meaningful because even for a new x, those W's are valid. That's the advantage of parametric model, right? In non-parametric model, I have a y here. So at best, I can get NT y's. I don't know what I will do with this NT y's to predict a new y for a new x star. Is it fine? It's making sense? So this is, we cannot work with this, okay? But this is the likelihood, there is no doubt about that. So another terminology or another concept from probabilistic machine learning, or rather Bayesian. The Bayesian philosophy states that whatever is unknown is to be modeled as a random variable. I'll repeat. In Bayesian statistics or in the Bayesian philosophy of doing things, whatever is unknown is random. There is nothing deterministic. And whatever is unknown is random, and you assign a prior for that random. The terminology I want to introduce here is prior. I'll repeat because this is new for most of you, except I can see one who has done the probabilistic machine learning. So yeah. So in Bayesian philosophy, whatever is unknown is considered to be random or uncertain and modeled as a PDF or whatever, right? Also, any prior belief you have about that random variable can be modeled as a probability distribution that is known as the prior. Okay. So let me write it down once more. So Bayesian philosophy whatever is unknown is considered random. Okay. And any prior belief is to be brought into the picture by using your prior knowledge. Okay. So the Bayesian philosophy is, I will repeat once more, whatever is unknown is random. Okay. And prior knowledge is included by assigning prior distribution over the unknown. That means whatever is unknown, you assume it to be random, but now even if it is unknown, you might have some prior knowledge about it. In that case, or that will always be the case, you assign or you model that prior knowledge using a PDF. I'll give you an example. Suppose in a problem the mass is unknown. I want to estimate the mass. So I'll assume mass to be random variable, right? Whatever is unknown is random. But I have prior knowledge about mass, it cannot be negative. That means I should model mass as a random variable and that distribution should be log normal. The distribution cannot be Gaussian or something, right? Even if it is Gaussian, you will shift the mean so much that it almost never goes to negative. Clear? If you know that, I'll give one more example. Tossing a coin. What is unknown? Probability of head. So I will assume probability of head to be random and model it as a distribution. The prior distribution, what will be the prior distribution? It will be some distribution which varies from 0 to 1. A popular distribution is beta distribution. So you assume the probability of success P, probability of getting a head, to be random because that is unknown, and model it as a beta distribution, and beta varies from 0 to 1. Clear? This is the idea. Now you can say, what will I do if I have no information? It is possible, right? Something is unknown, you are modeling it as a random, but you have no information about it. It's also possible. In that case, there are specialized prior known as non-informative prior. So you will model it using that non-informative prior, which will give you no information but is a probability distribution. That is the whole philosophy. For example, it's not a non-informative prior, but I'll give you one example. If you assume something to be uniform in some range, your prior knowledge is it is in that range, but you do not know anything about that. That's why it's uniform. Everything is equally likely, right? But uniform is actually not a non-informative prior. There are others, but I will not go into that. That's not needed. The main thing I want you to remember is whatever is unknown is random, and we will assign a prior on that based on our prior knowledge. Now in this likelihood or in this whole model, what is unknown? Y is the primary unknown thing. Epsilon is also unknown, but epsilon has already been modeled as a Gaussian distribution, so it's already a distribution. Yes, the distribution parameter is unknown, but that we will not touch. Y is the primary thing that is unknown. We will assume Y to be random and model it as a distribution. Now what is Y? Scalar vector. What is Y? Think about it. Look into this equation. Why is a function? It became vector because I have t at some locations. I have only finite measurement. That's why I was modeling it as a vector. Because x is vector because I have measured x at finite location. But in reality, y is a function, right? That's why I've written y bracket x. How can it be a vector when I'm writing y bracket x, right? Y is the function. I'll need to assign a prior to y. What is a vector? T is actually also x. See, T ideally is x. So this model is not vector. When I'm writing this distribution, it is becoming vector because this is probability of d given theta. So T is the target. It is over all the thing, but I have finite number of T's because I have finite measurement. So that's why when I do the likelihood, I write probability of d given theta. D is my measurement. That's why at this point it is a vector because these are those measurements. So maybe to clarify it, I should put a line here, right? So that will clarify it, right? Okay. So in this expression, actually t is a function. Okay. So y is a function. Y is unknown. So y is a random function. And we'll need to assign a distribution over this random function. What will you do? What prior? Obviously, we're talking about Gaussian process. I'll not assign Poisson prior. I'll not assign Poisson process, right? I'm talking about Gaussian process. So my prior will be Gaussian process. I mean, that's obvious from the title or what we are discussing, right? So using this philosophy, we assign a GP, Gaussian process, as prior to y. So basically, y is a sample or GP. Now GP is parameterized by mean function and covariance kernel. We will assume 0 mean. You can assume other mean also, it is done, but 0 in most cases works. Okay. Yes. Why can't you?
If we consider the starting itself, combining in the Gaussian process itself, the epsilon
because that means you are not assuming that you are going by the assumption that your model is perfect. You are saying t equal to y is the Gaussian process, right? That's what you are saying. That means you are saying that your model is perfect. You can never have noise in your data and all those things. It's not a realistic thing. Is the simulation perfect? Is the simulation not having error? Not necessarily. You might want to improve that. Obviously, I mean, Gaussian process is not only for simulation. First of all, whatever you have, that is having noise. Now you can give the same argument that okay, it is noisy, but I am happy with my noise. I mean, because my experiment is quite accurate. I am doing a DIC. But then I am also happy with doing an interpolation. I need not do a Gaussian process. I am happy with response service method. I did not learn the Gaussian process. I can explain that in an arbitrary manner will make no sense, right? The reality is your model, your data is noisy. Your data is not perfect no matter what you do. Even if you are doing an analytical way, your model is not perfect in that case. Is your model perfect? Is your RANS perfect? If you're never doing DNS, let's say, with the are you sure your initial condition is perfect? Because initial condition will come from some measurement, right? So that I can always extend. Okay. Yeah. So y I'll assign as a GP, I said, a mean function. So let's say a 0 mean function and a covariance kernel, right? K. How many inputs are there to covariance kernel? 2, x comma x prime. which are both same, but what you said was covariance matrix. Right now I am in a function mode, so there is no matrix. So this dot means input. Two inputs means two dot. And then what are the other things in covariance kernel apart from the x and x dash? We discussed last time. Length scale parameter and process variance. Those are unknowns. I told last time, right? That those you will not know. How will you know that? So that means theta. Okay. So we assigned a prior. Your prior is a Gaussian process. And like a Gaussian distribution, a Gaussian process is parameterized by the mean function and the covariance kernel. The mean function I have taken to be 0. So that's why there is no parameter. Otherwise, the parameter will come even in the mean function. And the covariance kernel, which is parameterized by length scale parameter from last time and process variance. Length scale parameter, the horizontal one, process variance, the vertical one, right? X1 and X2 is actually originally X and X dash. I mean, those are different notations of it. So, and theta is the length scale parameter and the process variance. Okay. Now, I just now said what is the role of prior? To encode your prior belief about the process. Here I did not care about my prior belief and said it's a Gaussian process. I said it and within 2 minutes I violated it, right? So if I have some prior knowledge, how will that come into picture here? Or is it like I'm totally violating it? No, I'm not violating it. I'll give you an example. Suppose your prior knowledge is that your function is periodic. Possible? In that case, this K will be a periodic kernel. So the choice of kernel will encode your prior belief. If your belief is that your function is like continuous, smooth, infinitely differentiable and all those things, then it will, a squared exponential kernel is what you will probably use. If you assume that your process is going to be non-stationary, then you are going to use a non-stationary kernel instead of a stationary kernel. So your prior belief in Gaussian process comes into picture through this choice of kernel. But you do not change the process because then the mathematics will change. So it's a balance between having prior knowledge and making things, calculations possible. I mean, I cannot take a process where I cannot do the calculation, then there is no point. So it's a balance between you want to encode your prior knowledge but also make it tractable, and that's why the Gaussian process part will not change. Everything is an approximation. Original prior, in this case, it need not always describe it exactly. It is possible it need not. For example, let's say your actual function is periodic and you choose to use a squared exponential kernel. In that case, your prior is not exactly representing the every original type of prior or every kernel. Okay. Okay. Not necessarily. But then that's why I said you can always, there are two things you have to keep in mind, that this theta is unknown. You are going to find it out. That means you are allowing your model enough flexibility that it can learn. So even if you are doing something wrong, the idea is that theta will be learned in such a manner that it will adjust. Even after that, if you are not happy, include a mean and make that mean that will be mean function. Make that mean parametric. So now there is a W transpose PCEX, I mean phi x. The mean is now a PCE, and on that there is a GP Even that case possible, right? So there are possibilities you can explore to make it more accurate, but the idea is that you will never change the GP assumption.
My data set, is the y value is true. That's, and I take mean to be 0. Would it happen that the variance will also be
Correct. True. It will happen. But so there is an important thing here. I am assuming my y to be probability of y to be my prior, right? But ultimately, when you will predict, because my ultimate goal is to predict, right? I will predict y star given x star comma x comma y. This will be also be a GP, but it will not have zero mean. Even if you start from zero mean, this will have a non-zero mean. So it will learn. Okay, and this we will see obviously next lecture. But I am starting from the prior. Prior is zero mean. Does not mean my posterior predictive will have a zero mean. It will have some non-zero mean. Okay. So I'll stop here. Any questions I'll answer obviously, but I'm not going any further. So I'll stop at this prior part. We have done nothing because Bayesian part I was explaining more. So next class we'll start from here. Yeah.
We have mentioned that scaling thing, in that where we can normalize the data and then we because normalization can bring the whole
Obviously,
scale to
all
zero.
those all those things you can do, but some think of a time series which is increasing. A increasing time series. Your y is y I plus 1, x is y y. Normalizing will be difficult, right? In that case. So you can always come up with examples, but that is not. Okay. Okay. Yeah. Strong knowledge about the prior. Yes.
so we know that the prior is not like a Gaussian. That's some other distribution.
Hmm.
Do we have alternate for Gaussian?
Probabilistic neural network, Bayesian neural network. Okay, there is something recently came up, like recent means 5 years ago, which is neural process. There are other ways of doing this, obviously. But remember, when I'm assuming it to be Gaussian, this Gaussian distribution is at each point. Remember the error bound? Each point it's a Gaussian, but this is not Gaussian. Each point. There is a Poisson process. Every distribution has a process, you can imagine like that. But the math will not be so easy. Because with Gaussian, as I was saying earlier, right, to him, that with Gaussian, if the joint is Gaussian, conditional is Gaussian, marginal is Gaussian, all those things are there. That is not true for any other distribution. So as a result, the calculations will not be simple, but there is a Poisson process.
We know the prior is Poisson, then we go with Poisson.
Poisson process is there, but there is nothing known as, or not many people use Poisson process regression. We are using Gaussian process regression, not Gaussian process. So equivalent to Gaussian process, there is a Gaussian process regression. If you know that it is not Gaussian at each point, you should not use Gaussian process, you will use something else. Or you can use a mean function, which will, what will it will do? The difference is now a Gaussian process. What does mean means? Assume the mean is a polynomial chaos. So the mean is probably like this, and each process point the discrepancy is now a Gaussian process. That also you can do. Add a neural network in the mean, then the discrepancy is a Gaussian. Everything is analytical. Analytical. So we will see that you will not need to use MCMC. You will not need to use sampling. Everything will come in closed form. The only optimization thing you will need is to find out this theta, that is. So it is very elegant. Mathematically, there are proofs you can do which does not exist for neural network. And it actually works for most problems. And most importantly, it is probabilistic, so it gives you uncertainty bound. So whenever it is not working, you know when it is not working. So those are all the advantages. Cubically, because this k will be inverted. So n by n, when you invert it, it is n cube. That is the bottleneck of Gaussian process, and there are methods that addresses this, like sparse Gaussian process, which I will not cover. But if you are interested, I covered it in the machine learning, the probabilistic machine learning. So it's there, you can refer that. But obviously here I will not cover that. But there are algorithms that addresses it. I mean, recently we submitted a paper where we brought this computation down to n log n kind of thing, which is very small, right? So it's possible. Yeah. Okay. Okay. So read about, if possible, go to the probabilistic machine learning and read about this prior likelihood thing. Although I'm covering it, but this is too much information I'm throwing at a time actually. So I'm trying to go slow, but even that slow is fast, I know that. So try to read those, that will help. Okay, thank you.